This video has to do with linearization, which I'm sure you've guessed has something to do with a line, right? Because that's its name. Anyway, I want to start off this discussion by going back over the tangent line. We've done a few tangent lines over the past few videos. I want to readdress that and kind of use that to launch off and then come back to this concept of linearization. So let's start off with one that's kind of relatively straightforward, I guess, for lack of a better description. So if you have something like y is equal to x to the fourth plus 3x squared, and you wanted to find the tangent to the curve at x is equal to -1, right? Now, to find a tangent line, you have to have, or any line, it doesn't have to be a tangent, but if you're trying to find the equation of a line, you need a point somewhere on the line, and you need a slope, right? So let's do those two things. So for a tangent, this is what we're trying to find. Okay, we need a point. So at x is equal to -1, we would substitute that into the original curve's equation so that we can find a point on the curve. So if you want a point on the curve, you use the curve's original equation. If you want a slope, you have to calculate the derivative. All right, and some students find it, there's just so much going on and there's so many moving parts, they find it difficult to remember what goes where. So remember, for a point, you're going to sub into the original curve equation, okay? And so when you clean this up, y turns out to be 4. So the point is -1, 4. All right? Now for the slope, you need the derivative. So what you would do is you would calculate the derivative. So, okay, so for the slope, you want the derivative. I don't know if this image of these written next to help. Sometimes you just never know what's going to help you keep up with a piece of information. There's just so much going on in Calc 1. It's really hard to kind of keep it all straight sometimes. So one of the techniques you might want to consider using is just making little notes as you go along as to what things go. So y prime is 4x cubed plus 6x when you take the derivative of this original function. So at x is equal to -1, y prime is 4 times -1 cubed plus 6 times -1. And students are always asking me, I have to show you this step? And I go, no, not if you're always right. Okay. If you're always right and you never make a mistake, do not show me this step right here. Right. But if you're wrong, if you drop a sign or something like that and you're wrong, then I can't give you partial credit as to what went wrong. Okay, so show me something so I can give you partial credit. Now this y prime is actually the slope. So the slope at this point is -10. So now that we have the point and the slope, we can use our point slope generic equation of the line, which you may not have seen, for college algebra, but we need it off and on during Calc 1. So y minus 4 is equal to -10 x minus -1. So when you clean this up, you get y is equal to -10x minus 6. Okay, let's go over here and look at the graph. So if you look at the graph, the red is this y is x to the fourth plus 3x squared. And the little blue line is our tangent. And again, this is the decimals. People let me use this, which I'm grateful for. So at -1, and this is kind of a strange scale, which looks like it's about right here, right? Then we would be up here, -1, right there, okay? So that's our -1, 4 spot, and that's where the actual tangent is. But you can kind of see it's a little difficult to tell exactly where that -1, 4 is. unless you're looking for minus 1, 4, because do you see how they're sort of superimposed almost right in here, right in this area? So for a little while in that area, they are so close together, right? They're so close together that you really can't, by the physical eye, see the difference between the curve, the x to the fourth plus 3x squared versus the line, right? And so this is the linearization of this curve in this area. So, somewhere between here and here, you can clearly see that the line and the curve seem to be following each other within some sort of acceptable tolerance, right? So this tangent line is sometimes called the tangent line approximation to the curve. And then in some cases, they, kind of shorten that down and just call it the linearization. So to be brutal, the linearization is really just our tangent line. Okay. So just sort of change the title. And when they ask you to find the linearization, just mentally translate that to, oh, I'm going to find the tangent. Now there's other things they're going to ask you about that, so let's kind of go a little further. But the tangent, the same exact things that you did to find the tangent are the same exact things that you need here. What we're going to explore next is, can you see that right up in this area and down in this area, the curve and the tangent line seem to start to diverge, right, and move away from each other. That's where a lot of the questions that you're going to be asked tend to focus on is, where is that? Okay, how safe are you to say, all right, I could, rather than to run a number through x to the fourth plus 3x squared, I could take that number and run it through minus 10x minus 6, which is simpler math, right? Maybe I'd be safe if it's one of these numbers. I don't know that it would be safe for one of these upper and lower numbers where it starts to diverge. So we're going to start talking about that. Okay. So the next question we're going to do is we're going to find the linearization, all right, and they could say f of x, it doesn't matter. F of x is equal to cosine x. And you probably notice sometimes I put the parentheses around x and sometimes I don't. I was trained to put the parentheses. The newer books have trained me to not put the parentheses, so it's sort of like, which one am I going with right now? Now we're going to find the linearization at x is equal to pi over 2. Now, a lot of my students, they're not real, I want to say, fluent or aware of radians. They're much happier imagining what the degrees look like. So they feel more comforted, more comfortable thinking of 90 degrees versus pi over 2. And you can make math equations accept 90 degrees as an input. A lot of times they use radians because radians is technically unitless. But it sort of depends, in my experience, on which subject you're in. For instance, in statics class, which I also teach, the equations are almost exclusively done in terms of degrees. And in math classes, it seems like once you get past trig, the equations seem to be almost exclusively done in terms of radians. But you can, switch back and forth. You have a conversion for that. All right. So let's do this time a linearization as opposed to a tangent. And let's see what we're going to do here. Okay. So if you want a linearization, you still have to have a point and you still have to have a slope. Okay. So the point is at x is equal to pi over 2, right? Y is equal to cosine of pi over 2. And hopefully you know what that answer is without having to go look at your calculator or at a unit circle, draw the whole thing. So hopefully you're comfortable with this. And this turns out to be 0. So your point is pi over 2, 0. Okay? Remember that goes into the original equation. Now for the slope, you need the derivative. So the derivative of cosine is minus sine x. And since we just came off implicit not too long ago, just remember if you accidentally loop back in, the derivative of x with respect to x is 1. Okay, so if you forget and loop back in, you're just going to put a 1 there, which doesn't change anything. Now, this is the slope. Okay, so the slope is minus sine of pi over 2. Right, and sine of pi over 2 is 1, because remember sine climbs, but then you have minus 1 because you have that minus in front of it. So here's your slope, here's your point, and you're back to y minus y1 equals m times x minus x1. So y minus 0 equals m, which is minus 1, times x minus x1, which is pi over 2, right? So y turns out to be minus x plus pi over 2, right? And we think this is the linearization. Now, sometimes what I suggest students do so that they can kind of start tying all these little loose ends together is to go, okay, so this is a line that's supposed to be touching the cosine curve, right, at pi over 2, 0. So technically what I should be able to do is, if that's true, I should be able to put pi over 2 in here and see if the points are the same, right? Because this came from the cosine curve. Let's see if we can get the same point from the linearization, right? Because this is the line. Okay, so if x is pi over 2, y would be minus pi over 2 plus pi over 2, and this is 0. Remember, it's kind of a sin to go sideways with all these equal signs. And so this is pi over 2, 0. Hopefully that's not being obscured by my face. All right, so we have pi over 2, substituted it in, minus pi over 2 plus pi over 2 turns out to be 0. So my 2 points are indeed coinciding. It just kind of makes you feel good about where you've got so far. Now, all this, let's talk about this. Let's get kind of real, because, sometimes you sit around and thinking, why are we doing this? All right, so I would have been actually just as happy if your question was pi over 2, 0 is that point. I would have been just as happy just to do pi over 2 inside the original equation, come up with 0 and be done. I mean, why are we going to all this trouble just to verify that, yep, they do touch at pi over 2, 0? I would hope the tangent line touches there. Well, let's show you what the beauty and the possibilities are in linearization. Now, keep in mind that you're in Calc 1, and that's pretty tough, right? But you can imagine to sort of think forward into the future, all right? And as you can imagine, the mathematics are going to get much more difficult. And if you're going into some line of work or degree, for instance, in chemical engineering, tons of nested inside each other equations, different kinds of physics courses, other math majors, whatever it is you're going into, you can imagine that the mathematics becomes very intertwined and very difficult to do a simple input through a very difficult nested together set of equations. So if we could find a simpler way to get a quick and dirty answer out of something, that might be well worth having, okay, for a very complicated process. So we're going to take a semi-complicated, just marginally more difficult process and reduce it to linearization. And you may not see that it was worth all that work, but I want you to keep imagining that what we're trying to do is to get you ready for the future. And in the future, you're not going to have just a level of difficulty 2 compared to a level of difficulty 1. You're going to have a level of difficulty 20 equation reduced to a level of difficulty 1. And that is a savings of your time and effort. Okay, so let's go. And here's the question of the day. I already knew that. Okay, the cosine of pi over 2 is 90. I had to memorize that back in trig. Let's try a different one. What is the value of f of x equal cosine x when x is 89 degrees? Just off there. Okay. So that one we don't know. We didn't memorize that one, and you're not allowed to grab for your calculator. Okay? So let's say you're somewhere where you don't have access to your calculator. I don't know. We're going to try this out. This particular math is a little bit more difficult than I would want to have with out a calculator, but trust me, I got all the way through calculus without a calculator because they were not financially available, okay, at that time. So you can do this, okay? You don't have to have a calculator on your phone or whatever. And I know I'm laughing, but y'all, you got to find your giggles, if you want to say it, somewhere along the line. You can do this. I keep saying you're tough. You're in Calc 1. You can do this without a calculator. All right, now here we go. So what we have to do first is this original equation was set up in terms of radians, right? So if you set it up in terms of radians, it has to be reused in terms of radians. So do you remember how to convert? If you have 89 degrees, remember that there are pi radians and 180 degrees, 2 pi radians and 360. So if I'm trying to get rid of the degrees, I put the degrees on the bottom, put the radians on the top. The degrees are going to cancel out. And when I reduce it, it becomes 22 pi over 45, which is not a number that I actually feel, terribly comfortable with. I was happy with the 89 degrees. All right. Now, so we had this lovely linearization, which said y is equal to minus x plus pi over 2, right? And here's the cosine curve and the minus x plus pi over 2. So right in this area is where we're at. So I go, well, y would be equal to minus 22 pi over 45 plus pi over 2, because remember this is our linearization. All right. So when you clean this up and you get a common denominator, I try to show you all these steps so that, if you're struggling with this part, it's easier to see the step and go, oh, okay, yeah, I'm still with you, as opposed to what just happened. So y is equal to pi over 90, which again doesn't really mean too much to me as a person. I mean, I'm kind of like, oh gosh, that's just 1/90th of the way, around the first top half of the circle. Right, and this turns out to be 0.034906585 whenever you get tired of dividing out. Okay, so this is what that value turns out to be. Let's check it on our calculator and see what it actually is. So this is the linearization result. Okay, and let's look at the calculator result. Okay, so cosine of 89 degrees turns out to be about 0.034899497. I just got tired of writing at that point. Now, those look pretty close, right? They're both 0.03, both got a 4 after it. Now, this one goes to 9, and this one is 899, which seems to be, pretty close. Okay. So what they generally do then is to say, all right, this is close, seems close enough to me that if you run it into this equation, I get a close enough answer to the actual answer. Now remember, what you're trying to imagine is, let's say that this is a level 1 difficulty. You could even say it was level 1 or 2 if you don't like dividing things out by hand. Level 1 or 2 difficulty equation to solve. But rather than this cosine thing, let's consider that you've got some sort of function that's really quite complicated. Maybe it's something that's been put into a computer, got multi-steps, they all feed into each other. There's, this one feeds into that one, feeds into this one. And this is a level of difficulty let's say, of 25. So the question is, do you want to by hand, okay, try to do a level difficulty of 25, or do you want to do a level 1 or 2? Well, I would think 1 or 2. And as a matter of fact, a lot of the things that you work with, like your calculator and stuff, they don't have exact numbers. They have linear approximations to things, and that's what they're kicking out to you, right? So, and if you're doing computer programming, you will probably do something where you're using linear approximations to approximate a much more difficult thing. That was probably an assignment they have you program. I had to do it, right? And it was just a minor of mine. So I had to program that in. Now, so what we need to see is something that says, well, it looks close enough. I mean, isn't it close enough? Okay, so they have what they call a percent error. So sometimes they ask you to calculate up the error between your calculated number, your approximation. Okay, so this one is an approximation, and this one is supposed to be more accurate. Okay, now, so how do you do that? It's the absolute value of, I don't think I'm going to be able to write all that in there, your approximation minus the actual one or the calculated one or whatever you want to call it. This is your list divided by the actual one that it's supposed to be if you had done the more complicated level 20 computation times 100 so that you can get a percentage, right? Now, because it's absolute values, it doesn't matter if you go, if you decide that you're going to do the approximate minus the actual or the actual minus the approximate, because you're going to take the absolute value of it. So whichever one you're subtracting, right, you're going to take the absolute value. It's going to turn positive anyway. Just remember that you're dividing by the actual one, not your linear approximation. So this is the linear one, and this is the original curve. I mean, whatever you want to say. Okay. So for this problem, it turns out to be 0.034906585. And people are going, these can't all be significant. And I'm going to tell you the same thing I argued with my chemistry, my chemistry teacher back in the day when I took chemistry. And I said, if I come up with this number, it's significant to me. Right? So if it's significant to me, why can't I write it down? And I'm pretty sure I did not win that argument. Right? And then as a 25 plus year teacher, I got conned by my students to sit in on a on a chemistry class all semester long because they kept telling me that it was way too hard, and I kept saying, so they had me sit in on this class. I won't go into the detail. Had the same argument with that chemistry teacher going, well, it's significant to me, except this time I was their boss. All right, but they still argued the part. So I get that. Okay, totally get that. Do not we're not dealing with significant figures right this second. All right. We're just dealing with math, and I'm putting all these in here just so that you can see them, and I think they're kind of cute. Okay, so this is 2.03 times 10 to the minus 2. After you do the math, you can fast forward through all the weird things I tell. Okay, so this says it's not a 2% error, because we already have a percent because we already multiplied by 100. So this is not a 0.02 where you're going to have a 2% error. This is already percentage. This is 0.02%. That's really tiny. I mean, that seems like something I could deal with. Well, it just depends, okay? It totally depends on what your tolerance is and what your wiggle room for error is. If this is somebody's, I don't know, you could think of some sort of a medicine or some sort of a dosage where 0.02% error might not be a good thing, right? I'm not a medical person, but I could see where, maybe that's not a tolerable amount of error for anesthesia or something. Um, maybe in something that you're building, you don't want to be off. I worked in no, I won't tell you where I worked. Okay, so we're going to move on. Okay, just assume that there are some places where you can't have that tolerance. Okay, that may be a little bit too far out of reach. Okay, now let's move on, and we're going to do another problem, and we're going to kind of get into this a little bit more in depth about this allowable error. All right. And just kind of bear with me. I know that for a minute you're going to be going, and we want to do this. Why? All right. So the linearization of f of x equals the square root of x plus 14 at x equals 2. And so in effect, if x was 2, right, you're taking the square root of 16, which we know is 4, right? And again, you're going, and the point of this is because your teacher asked you to do this and it's 5 or 6 points on the test, all right? So, but keep in mind, in the future, this is going to be something you're going to use where you take a level of difficulty 10, 15, 20 and reduce it to a level of difficulty of, 1 to 2 or 3 or 4, all right? So here we go. Now, to do the linearization, I need a point and I need a slope. Okay, so for the point when x is equal to 2, y is equal to the square root of 2 plus 14, which is the square root of 16, which is 4. So your point is 2, 4. Okay, now for your slope, you would say, I need to take the derivative. So the derivative, you bring the 1/2 down, because remember this is x plus 14 to the 1/2, right? So you bring the 1/2 down, leave the inside alone, take 1 off the power, so it's going to be minus half. Loop back in and take the derivative of the inside, which is just 1, because the derivative of x with respect to x is 1, and the derivative of 14 is 0. Okay, so this is the slope. So at x equals 2, the slope is 1/2, 2 plus 14 to the negative 1/2 power. So this is 1/2. This negative power says it's not happy, wants to go the other side of the fraction bar. So it's 1 over the square root of 2 plus 14. So this is 1/2 times 1/4, because the square root of 16 is 4. So this is 1/8, right? So you have the slope is 1/8, 1/8, and the point is 2, 4, right? And you go y minus y1 is m times x minus x1. So y minus 4 is equal to 1/8 x minus 2. And when you clean this up a bit, you get y is equal to 1/8 x plus 15/4. Okay? And if you want to, you can substitute x's 2 in here and see if you get 4 back out, just to check your math. Sometimes people make mistakes when you've got, different negatives over here or whatever. Okay, and here we go with a question. So using this linearization, let's look at the drawing for a minute. Okay, so the red is that square root of x plus 14, and the blue is my linearization. So you can kind of see that, I don't know, between here and here, right? Somewhere between here and here, they follow really close to each other, right? And what we had been doing is saying that if x is 2, when you substitute 2 in, 2 plus 14 is 16, square root of 16 is 4. So this is actually where the tangent line was calculated, right? And what we're saying, I hope this is kind of getting across to you, is we're saying that, somewhere in the vicinity, I don't know where that is, okay, somewhere in the vicinity of the number point that we calculated the tangent or the linearization at, okay, somewhere on either side of that, there's not that much difference. And so we could find, using the line equation, we could find values for x's that, kind of in that area. So maybe x is 2.01 or maybe even 3, right? Because 3's up in here. That looks like the actual line, and the curve are this close. Okay, maybe we could do 0, right? What if x is 0? So it looks like some of these x's that are in here, we could actually run them into this line as opposed to trying to figure out the square root of that number and get an answer, right? That's what we're trying to do, right? So this is my linearization, and it's saying within the vicinity of x is equal to 2, somewhere on either side, okay? You might be able to use linearization to get close to the number that you would get if you ran the square root of that number. So let's try a couple, right? So what if I wanted to figure out what's the square root of 15.98? Now originally, right, we set this up as the linearization to x plus 14. Okay, so this is where we started. We found the linearization to this. And they are asking me about 15.98. And I need to make 15.98 look like x plus 14. Okay, so wouldn't that be, let's just take the 14 out. Okay, so if we take, because I'm looking for this pattern, some number plus 14. So that would be 1.98 plus 14, right? That's 15.98. So you're looking for this pattern and you're replicating it with the number that they're actually curious about. And then you're going to use this and substitute it into the linearization, because 1.98 is fairly close to 2. Let's see how close we can get. So now we're going to say, all right, so we're going to sub 1.98 into y is equal to 1/8 x plus 15/4. Okay, so I'd have y is 1/8, 1.98 plus 15/4. And when you multiply this all out and add it all up, you get something like 3.9975. And this is the linear approximation. Now, this would be actually maybe what you would do for your work. You'd come up with this linear approximation equation for a line, and then they would ask you to use that to approximate maybe future values or quantities or different kinds of rates, perhaps, or whatever. But for right now, just for us, okay, let's see what our calculator would have told us about the calculator answer to the square root of 15.98. Okay, so we're just doing this for comparison. This would actually be the linearization value. Okay, but let's see how close we actually got. Okay, so the square root of 15.98 according to the calculator is 3.997499. And I'm sorry, but that's pretty darn close, right? I mean, isn't that really close? Let's do a percent error. Okay, so it is 3.9975 minus 3.997499 over 3.997499 times 100. So this is 1.9555 times 10 to the minus 5. So you've got 0.1234195. Okay, now think of this. This is a percentage already. That's a very low error percentage. I mean, extremely low. I think that's pretty good. All right, let's try one more. Okay, let's just try, just for grins, to estimate using our linearization the square root of 15.9. Now remember, all we had to start with was we started off with the linearization to the square root of x plus 14 at x is equal to 2. So we have to see if we're somewhere in the vicinity of 2. So we have to try to manipulate 15.9 into x plus 14 and see what we've got. So what you would have is, if you have to have this plus 14, 15.9 becomes 1.9. And 1.9 seems to be in the vicinity of 2, right? It's actually closer than where we just were. So we had our equation where we have y is equal to 1/8 x plus 15/4. And this time we're going to use 1.9. So I got 3.9875. And when you do the actual calculation and then you're going to do the percent error, okay, I got 3.9875, and the calculator answer turned out to be 3.987480. This is using a calculator. Remember, the bottom number is these. Let me write this out. These two match. You have to divide by what the actual calculator is. And this turns out to be 0.000497. Okay? Now, so this is, I think I may have earlier said this was actually closer. Now that I'm thinking back about what I said. If I did say that, I'm sorry. This 15.98, 1.98 is closer to 0 than 1.9. So if I said that, I beg your pardon. I'll go back and review it. If it did actually say that at some point later on, I'll redo this video, but it's not closer. Sorry. All right. So this is a slightly larger error because I'm slightly farther away. All right. Now, percent. Why are we doing this? Okay. Let's go back up here. I'm just trying to show you that we can be really close with a low error percent. And this is the whole beauty and usefulness of this linearization, is that if you are somewhere in the vicinity of the area of where you set up the linearization, you can use that and get numbers that are really very close to the actual number. All right. Now, the question begins to become, how far away can you actually be? All right. So that's the big question. How do I decide how far I can be without it having an intolerable margin of error? So they set up an equation that goes kind of like this. So what if we're willing to live with a difference? Now this is not an error rate, just a difference in value between the linear approximation and the calculated using your calculator and the very intricate level 20, 25, 40 calculation that you're looking at in the future of 0.1. So I can live with a difference in value between those two values of 0.1, but I can't deal with 0.1 or bigger, right? So what you're saying is, and it doesn't really matter which way you subtract them. Okay, 1/8 x plus 15/4 minus the square root of x plus 14. Now, right now, this is my linear approximation. And this is my calculator, or level 20 calculation. So this would be like level 20 in difficulty. And this would be like level 1 or 2 in difficulty. So, and it doesn't matter which one you start with, because you're going to take the absolute value, and it has to be less than 0.1. Because the difference between the two, remember that's what I said, I can live with a difference between the two. Now, keep in mind that 0.1 doesn't sound very big, but if it's like 0.1 of $1 billion, that's a lot of money. I would take 0.1 of $1 million, all right, or $1,000. I'd be happy with that. All right, now here we go. Remember algebra? Minus 0.1 is less than 1/8 x plus 15/4 minus the square root of x plus 4 less than 0.1. Remember when you had absolute value inequalities and it looked like this, you say it has to be, but then 0.1 on either side, all right? So then your linearization, you add, this is supposed to be 14. You add the square root of x plus 14 to all three sides. Okay. All right, so what this is saying is that the linearization, and this sounds like, well, I kind of knew that, has to be within the actual value plus 0.1 or the actual value minus 0.1 in order to meet my criteria, right? So what are we going to do with that? All right, so let's look, and I plotted these off so that you can see. And so here's the original function plus my tolerance, and here's my original function minus my tolerance, right? Plus or minus 0.1, okay? And then this is my linearization, right? So if you look over here, the red curve is this plus my tolerance. The purple curve is less my tolerance. And the blue line in the middle is my linearization, right? And do you see how I'm going to have to slide it back and forth. But do you see, let's follow the blue line. Do you see how the blue line intersects right here with that upper limit, the plus 0.1? Okay, then it falls in between the two curves, falls in between, falls in between, falls in between, and then down in here it intersects again. Never touches that bottom curve, right? Never touches the minus 0.1. It does intersect the positive 0.1. Now, I ran these on my calculator to find out what those values were. And this point of intersection is minus 4.303, 3.014. And this one is 9.955, 4.994. Okay? So what we are looking for is what values of x, okay, are in that tolerable range of plus or minus 0.1. And so this is where it goes out of range. See where it starts? I don't know if you can barely see it, but right in here, it's starting to diverge. And right up in here, it's going to start diverging. All right? So how far off can you be? Well, you can be between minus 4.3 to 9.9. So round, don't go, if this had been 9, don't go 9.96 round up to 9, well, to 10. That would eventually round up to 10. Don't round up because we want it to be less than 0.1. So to be conservative, you need to undercut it just a little bit so that you're definitely within the 0.1. Because if this is some sort of life and death situation or billions and billions of dollars, you don't want to be over your limit. Okay? So as long as my x is in between minus 4.3 and 9.9, so remember my x was this x plus 14. So if I'm trying to find the square root of numbers where x is between minus 4.3 and 9.9, right? Then this is a good approximation to do 1/8 x plus 15/4. Now technically, okay, the hair on your arm should be standing up, okay, going, oh my gosh, if this was like a humongously difficult problem, that's an amazing thing to know, right? And so I think that is something that could hold up for you in the future and something that you need to know. So you just have to kind of think of the beauty of this because let's say that x is minus 4.3. That's as low as I can go on the bottom. Then the square root of minus 4.3 plus 14 using your calculator is 3.1144. And using your linear approximation, you get 3.2125, and the difference between these is 0.0981, which is less than the allowable tolerance that you said you could live with, of zero point 0.1. So can you kind of look into the future and imagine that if you could take something complicated that takes pages after pages after pages to compute, or yards and yards of computer programming language entries, and you could compute a reasonably accurate answer with one step. That is cool. Okay. Now, I tell you all these things, and I often tell you little weird stories in between so that you'll take a break and kind of let your brain relax. But I just want you to kind of let your brain relax here for a second and go, okay, so it is really a tangent. Okay. But the things that you can do with it, you know, in the future, where you're taking terribly complicated, massive calculations and reducing them to a line, that's just absolutely fantastic and could really save a lot of time. So this has hidden capabilities, hidden secrets. I hope this kind of helps you a little bit to see what the beauty of this is, and I'll see you at the next video.